All right. Good afternoon, everyone. Hope all is well. Hope everyone is doing all right. So hope you had a great weekend as well. So we're going to get into 7.4 today, close out chapter 7, and talk about how we're going to move forward from there. So 7.4 is the addition and the complement rules. Talked a little bit about the complement last section. Going into more detail in this section. So the complement of your event is a set of all outcomes in the sample space that are not in that event. Kind of inappropriate. You see our complement rules. Really, it's just one rule, but just changed according to what you're trying to look for. If you have the probability of your event and add it to the probability of your event not occurring, that should equal out to give you one. So that means if you're looking for the probability of your event not occurring, just subtract the probability of your event from one. Or if you don't have the probability of your event, but you do have the probability of your event not occurring, subtract that from one to find the probability of your event. Go up on the blue. All right, so if you are dealt one card from a standard 52 card deck, find the probability that you are not dealt a queen. Okay with that purple. All right. So to find the probability of not getting dealt a queen, you can first find the probability of getting a queen, and then from there subtract it from one. So we talked about that scenario already. We know there are 52 cards in the deck. There are 4 queens in the deck. So the chance of getting a queen out of the standard 52 card deck is 4 out of 52. And then you can reduce that down to 1 over 13. Going up on the green. So find the probability of not getting a queen. You'll do 1 minus 1 over 13. That 1 turns into 13 over 13. So whatever the denominator is, that's what that 1 will turn into. And then you subtract 13 minus 1, which will give you 12 over the 13. If I go up too far, let me know. All right, so circle graph shows the breakdown in minutes for various aspects of an average 190-minute NFL TV broadcast. What is the probability that a minute of the broadcast is not devoted to game action or actual football? So I got a little circle graph under this, just giving everybody a chance to finish. On that red, on with the red. All right. So you see, for those who do watch football, you see this is the breakdown, supposed breakdown of a 190-minute football broadcast. So you see 15 minutes full of replays, 63 minutes of commercial, 67 minutes of shots of players just standing around, 34 minutes of coaches and crowd, cheerleaders, etc. And then there's only 11 minutes of actual game action. So we want to know what's the probability of the minutes that you would look at that's not devoted to game action. So probability of getting a minute that's game action, it's 11 out of the 190, because all of that is 190 minutes in total. Then we'll subtract that from 1. So that 1 turns into 190 over 190. 190 minus 11 would be 9 over 90. Hold on the red. All right. We have another circle graph. This one shows the distribution by age group of 214 million car drivers in the US, with all numbers rounded to the nearest million. If one driver is randomly selected from this population, what is the probability that the person is less than 80 years old? All right. Here's the circle graph for this one. All of these add up to 215 million. We just look number 214 million. All of these numbers add up to 14 million. But notice we want to know the probability of getting a person that's less than 80 years old. This 8 million right here represent all of those who are 80 years old and greater or older. So if I want to know the probability of getting someone that's less than 80, I'm going to do 1 minus the probability of those that are 80 and older. So that's 1 minus 8 over 214. That 1 will turn into 214 over 214. And then 214 minus 8 is 206. And then that can reduce by 2 to be 103 over 107. All right. Next thing is mutually exclusive events. Let's take us to our addition rules. So 2 events are mutually exclusive if it is impossible for both events to occur simultaneously, or when you look at both events, they do not have anything in common or any outcomes in common. All right, so the formula for 2 mutually exclusive events, if you want to know the probability of, let's say if our events is A and B, we know the probability if A or B will occur. You take the probability of A and add it to the probability of B, and you're good to go. Looking for the probability of A or B occurring. One for black. So if one card is randomly selected from the deck of cards, what is the probability of selecting a king or a queen? All right. So first thing we want to ask ourselves, are the events mutually exclusive? And the answer would be yes, because they do not have any cards in common. We're looking at kings and queens. So there are no kings that are queens and no queens that are kings. So they don't have anything in common. So we would find the probability of both of them individually. What's the probability of getting a king out of the deck? It's a 4 out of 52 chance because it's 52 cards, 4 kings altogether. How many queens are there? 4. So it's a 4 out of 52 chance of getting a queen as well. So since they're mutually exclusive, we can go ahead and add them together. 4 over 52 plus 4 over 52, which will give you 8 over 52. And reduce that down to 2 over 13. All right. Those are mutually exclusive events. Now, if we have events that are not mutually exclusive, in other words, they have something in common, here's the formula for that. If we know the probability of A or B occurring, but they do have something in common, you take the probability of A plus the probability of B, and then minus the probability of A and B. In other words, what they have in common. And we'll see why that's the case in a second. All right. By holding on to that purple. All right. So in a group of 25 baboons, 18 enjoy grooming their neighbors, 16 enjoy screeching wildly, while 10 enjoy grooming their neighbors and screeching wildly. If one baboon is selected at random from the group, find the probability that it enjoys grooming its neighbor or screeching wildly. All right, so these events are not mutually exclusive because we have that and there. We have those that enjoy grooming their neighbors and screeching wildly. That means they're in common with both categories. So I'm gonna call G, event G, grooming your neighbors. And then for screeching wildly, gonna use W. Remember, we don't want to use S. S represents our sample space normally. Anybody holding on to green as I scroll up? So these are the probabilities for all three pieces of the formula. We have those that enjoy grooming was 18 out of the 25 baboons in total. Then screeching, 16 out of 25. And then grooming and screeching was 10 out of 25. Scrolling up. Now that we have all three pieces, we can plug them into the formula. That's 18 over 25 plus 16 over 25 minus 10 over 25 gives us 24 over 25. And so notice also I didn't reduce the fractions up here. Well, I know we could have reduced it right here, but you don't reduce them to the end. That's just easier practice. Just go ahead and keep them as they are. Do your calculation, then at the end, reduce it. Don't want to change denominators and stuff and then have to change them back. So it's the best way to do it. On to the next one. Everybody holding on to the red. So here we have the chart. Just the marital status, U.S. population ages 15 and older in 2015 and it's in millions. So it says if one person is randomly selected from the population represented in the table, find the probability that the person is divorced or male, person is married or divorced. All right. So let's look at the first question. It says the person is divorced or male. We know what's the probability of choosing someone that's divorced or male. So we look at our categories here. We have divorced here, and then male is here. Total number of people altogether is 254 million. And there are total 123 males, 123 million males, then 26 million divorced people. So also recognize when we look at our two events, are the events mutually exclusive or not? The answer is no, they're not mutually exclusive because you can be male and divorced. That's 11 million right here of those who are male and divorced. All right. So when we go to our probabilities, we need three pieces because they're not mutually exclusive. We do have a category that's both of them. So that's going to be 26 over the 254. There's 26 million altogether that were divorced, 123 male altogether over the 254, and then there are 11 that were divorced and male. Once you have your three pieces, and keep in mind, this chart actually shows better why we have to subtract this and category. If you go here, notice that this 11 is included as a part of this male total of 123 male. But this 11 also is included as a total, this divorce total of 26. So if you don't subtract what they have in common, that means you will be counting them twice, that 11 twice when you add up the 26 and the 123. So that's why we have to subtract the 11 over 254. So it's 26 over 54 plus 123 over 54, 254 minus 11 over 254, which gives us 138 over 254. We can reduce that by 2, and that's 69 over 127. And the math lab wants, that's the math lab, WebAssign wants the decimal, it's 0.54. All right, very good. Now the next one, person is married or divorced. Now, if you look at the way this chart is set up, nowadays, relationships be redefined and everything, but being married and being divorced are two separate categories. They're not mutually exclusive. You cannot be married and divorced. You're either married or divorced according to this chart right here. So they are mutually exclusive events. And so we can go ahead and just find the probability of being married, probability of being divorced. That's 133 over 254. There were 133 total that are married, 26 total that are divorced out of the 254. Add them together. That'll be 133 over 254 plus 226 over 254. Ultimately give me 159 over 254 or 0.63 as a decimal. All right. Couple more and then we'll be done. Just want to reemphasize the process. Anybody holding on to the red? So we have a single dice toss, find the probability of rolling an even number or a number less than 5. All right, so when it comes to rolling the die, we know that there are 6 numbers in our sample space. Out of those 6 numbers, 3 of them are even. That's 2, 4, and 6. There are 4 numbers that are less than 5. That's 1, 2, 3, and 4. And we see that these events are not mutually exclusive. They do have something in common. They have the numbers 2 and 4 in common. So 2 and 4 right here, and 2 and 4 right here. So being an even number and less than 5, and the numbers 2 and 4, so it's 2 out of 6 as far as that probability is concerned. Roll from purple. All right, now that we have all 3 pieces, put them in the formula accordingly. 3 over 6 plus 4 over 6 minus 2 over 6 will give us 5 over 6. One more. Got a single card is drawn from the standard 52 card deck. Compute the probability of drawing a king or drawing a diamond. Anybody holding up? Don't know if it would die. So are these events mutually exclusive? The answer is no, because there is a king that is a diamond. It's the king of diamonds. So we just need to find the probability of each one of those three pieces individually. So there are four kings in the deck. So it's 4 out of 52 for the king. There are 13 diamonds, so it's 13 out of 52 for diamonds. And then there's one king of diamonds that's in common with both categories or both events. So it'll be 1 out of 52. All right, so finish it off. We'll put our three pieces in the formula. 452 plus 13, 452 minus 1 over 52 gives you 16 over 52, and that reduces by 4 to give us 4 over 13. All right. So that's it for 7.4. Right now, all of your assignments are open, so make sure you take advantage of that. Next class will be a review class. I will not cover anything new. So you can bring your questions. If you don't have any questions, you don't have anything for me, you don't have to show. But I will show up. I guess I'll give you 15 minutes. So whoever show up, if you don't show up, don't nobody show up, then I'll go ahead and go on. But I will be here at the appointed time. So if you have any questions, make sure you bring them on next class. And like I said, we about to close out the semester. Everything's open. The next due date is the end of the semester. So make sure, we do what we can to get caught up and get our stuff, to where we want it to be. Well, we have fifth week grading and we have 10th week grading. So I need to finish out 10th week grading. Fifth week and 10th week don't really matter. They're just like progress reports. Now the third grade that I put in will be your final grading. And that's the one that's going to stick to your transcript. Yeah. But that don't go in until like December, whatever that date is I put in there. All right. Any other questions before we close out? All right. You guys have a good one.